Yay! More stats, more examples. This video is to go over goodness of fit. So goodness of fit we use when we're trying to figure out whether or not our data set matches a specific distribution. It can be any distribution, the normal distribution, a distribution laid out by a different data set, or commonly it is a uniform distribution if we're trying to figure out whether or not data is random. Random data should fit the uniform distribution when we're looking at the last digit. If it's truly random, then every single digit, 0 through 9, should appear essentially the same amount for a data set. So that's what we're going to look at for this Barry Bonds example. We're going to go through all 8 steps per the hypothesis test, and we're going to look at how to do the calculations in Excel. So let's get started. Okay, so here is our example. It's a goodness of fit example. The table presents the last digit of the measure of Barry Bonds' home run distances. The value of 0 seems to occur considerably more often, but is it actually significant? Meaning, does 0 come up so often that it seems like these numbers aren't random? Since they aren't random and they're coming up too often as 0, and 5 comes up quite a bit too, it's likely that they're being rounded. Because when we round a value, say like weight, we don't say I weigh 123 pounds. We say I weigh 125 or 120 or 130. We round it to a number close to what we weigh, but we typically just weigh it to the 0s and 5s. The same thing would happen when we're collecting data. If we're not actually measuring it, we're just kind of rounding. We would say it went 150 feet, or it went 200 feet, or it went 175 feet, or it went 180 feet. But we wouldn't be giving the actual numbers. That would be more random, like 183 feet, 184 feet, 181 feet. So when we see the number 0 and 5 come up a lot in our data, it should be a red flag that the data was not actually measured, and it was either recorded by asking people what they weigh instead of weighing them, or estimating the distance instead of actually measuring it. So let's go through this test and see whether or not this 0 comes up so much that we can say this doesn't fit the uniform distribution, and it was not actually measured and was estimated. Okay, so our first step, if we look at our 8 steps over here, is to ID the claim. So right here it says, test the claim that the digits do not occur with the same frequency. So let's go ahead and write down that claim. I'm so impressed that it says claim and not clam, you'll have no idea. Excel does not spell check, so half the time these are going to come up as clam. Let these go away real quick because we don't need them yet. Okay. So our claim is that the digits do occur with the same, the digits do not occur with the same frequency, which was given right here. The opposite of that is the digits do not occur with the same frequency. So, except that it's going to be do. Sorry. Okay, so if the claim is the digits do not occur with the same frequency, then the opposite would be the digits do occur with the same frequency. And you may be thinking, well, the instructions over here say that we're supposed to use math symbols to identify these, but we've gone into categorical data, and when we do that, it makes it more difficult to write it in math symbols. So we'll find ourselves often writing what we used to write, which is symbols and abbreviations, with full sentences, which is good news and bad news. If you're really not a big fan of all the abbreviations and all the symbols, then yeah, you don't need them for this. But if you're not a big fan of writing a lot of stuff down, then these particular hypothesis tests get a little wordy because we lose our ability to just write something like mu equals 5 or sigma equals 3, and we have to start writing down entire sentences. Okay, step 3 is to write the alternative and null hypothesis. So the null hypothesis and the alternative hypothesis, because we're given categorical data, are set. We no longer have to figure out that which one is equal and which one is not equal to be able to figure out which one is the null and the alternative. For these kinds of examples, the null and alternative hypothesis will always be the same. The null will be that they match. The last digit matches the uniform distribution. And remember, the same frequency means the uniform distribution. And the alternative will be that they do not match. The last digit does not match, fix that, the uniform distribution. Okay, so this will always be the case that the null hypothesis will say that they match and that the alternative hypothesis will say that they don't match. What will change is whether what the data set is. So in this case, it's the last digit. So you'll have to get whatever data set you're looking at. And what distribution it is. In this case, we're saying that they're all the same, so it's a uniform distribution. But in other cases, it might be a different distribution, like the chi-squared or the normal distribution. Or if it's just a distribution that matches a different data set, then you would just say the given distribution. Okay. Step 4 is to identify the significance level. And this says to use a significance level of 0.05. So that would be the significance level we use here. Alpha is 0.05. Step 5 is to identify the test statistic equation and function for Excel. So here we're going to write down all of our functions for Excel. So for p-values, we're going to use the chi-squared distribution. For the critical values, we're going to use the chi-squared inverse. And the degrees of freedom here will be k, which stands for categories, minus 1. And our two equations will be given by this very large chi-squared equation, which essentially says take what we observed and subtract what we expect to happen and square it, and then divide by what we expect to happen. And then what we expect to happen is given by this equation n divided by k, which is just the number of things that we counted divided by the number of categories. If we're saying that they all have the same frequency, then what this is doing is adding them all up and dividing by the number of categories, because each category should have the same. So in other words, if we have 10 pieces of data in 10 categories, then each category should get 1 piece of data. Okay, so let's focus on getting these two equations calculated, and that we're going to do in Excel. So scrolling up and creating this next to our data set, just to make it simple, we'll make a column for E, and then we'll make the chi-squared column. So this will be the O minus E squared divided by E. Okay. So for E, we're going to do n minus k. So that means we have to sum all these up. So I can highlight this, and it will sum them to 81, which you can see down here in the corner, maybe, but it sums it to 81. So E will be 81 divided by the number of categories, which is 10. Because I have the last digit of a number, there's always 10 for the last digit of a number, 0 through 9. And it will be the same for all of them because I'm trying to match the uniform distribution, so they should all be the same. Now I've got to do this calculation, which is the difference between my observed and what I expected. And before we even do the calculation, I'm looking at this 47 minus 81. When I do that subtraction, I'm going to get a pretty big number, somewhere around 40. Okay, and then I'm going to square it, so I'm going to get a really big number, and then I'll divide by the expected value, which is not that big. So I'm going to end up with a big number, so I'm probably going to get a really big summation. Okay, so let's try it out. This is equal to, open parentheses, observed minus expected squared divided by expected. So it's blue minus red divided by red again. Okay, so I did get a big number like I was expecting. If I carry all of those down by double clicking with the skinny arrow or dragging down, then I will get all of the differences squared divided by the expected values. And remember, the actual chi-squared value, the test statistic, which I'll abbreviate TS, is equal to all of those added up. So I'm going to do sum and then highlight all these numbers. Pause for a second so that you can see that, and then hit enter. If you'd like to see these equations, I'll grab them for you. This one was G minus H4 squared divided by H4, and that's because I was in H and 4 and G and 4. So it would match wherever you are on your Excel spreadsheet. And this one was just the sum of the column I for me, but what really matters is that it's the column where you've put this title. Okay, so I have my test statistic, it's 221. I'm going to go back down to step 6, which is where I calculate the test statistic, the p-value, and the critical values. Okay, so let me change this font color. So I've got a test statistic, a p-value, and a critical value. Here we go. Our test statistic is equal to what we figured out over here. I'll just grab it, 221. That is a very large test statistic, and you can see it was rounded just due to the size of the box up there. So we've got a couple more digits to work with here. Now, you may be wondering Is this a right-tailed test or a left-tailed test or a two-tailed test? Because we usually need to know that to be able to figure out p-value and critical value. So we have to go back up and look at the alternative hypothesis. That's always how we figured it out before, so let's go look at it. Usually we go to the alternative hypothesis and we say, well, if the alternative hypothesis is do not equal or left or right, then that helps us decide what tail we're in. But there is no math symbol in our alternative hypothesis now. So how do we decide which tail we should be in? So to help us decide if we're right-tailed, left-tailed, or two-tailed, we have this flow chart. And we'll see that the result of this flow chart is that we're always right-tailed. So if we compare the observed and the expected frequencies, and we get a really big difference, then we want to be able to reject the null hypothesis, because the null hypothesis says they're the same. But if we do the subtraction and we get a really big difference, then the difference is saying that they're different because because the difference is large. I know I just said difference like 3 times in a row, but it's fine. When I do subtraction between two numbers and I get a really big number, then those two numbers didn't have very much in common. They must have been far apart. It's literally the difference between the two numbers. And so if they're far apart, they likely don't match. So I want to make sure when I get a big difference, I end up rejecting the null hypothesis. So that means that I want to reject the null hypothesis when I end up on the right-hand side, because that's where big numbers live on the number line. So we follow this. If it's a small chi-squared value, we would get a large p-value, and we would want to fail to reject h0. A small chi-squared value would mean that the difference is small, so the numbers are closer together, so it's more likely that they match. Over here, a large chi-squared value and a small p-value, then we would reject the null hypothesis because the difference was large, so the numbers were far apart, so it's not likely that they match. So in other words, this test is always a right-tailed test. Going back to our Excel spreadsheet, we're going to write this down and we're going to find the p-value and critical values. Okay, so we're going to calculate the p-value for a right-tailed test. So we want to use the chi-squared distribution on the right and the chi-squared inverse function also on the right. So let's go up and edit this because that was missing. And we'll edit this one. We need both of them on the right. Okay, so p-value is equal to chi-squared on the right, our test statistic, which is right here, and our degrees of freedom, which is K, which stands for categories, because we already used C for something else. So the number of categories is the number of last digits, which was 10. So K minus 1 is 9. And that would give us our p-value, which is super duper tiny because we have such a large test statistic. And our critical value would be given to us by chi-squared inverse on the right. We need our probability, which is the size of alpha, which for this problem was 0.05. And our degrees of freedom is again 9. And we can see that our critical value is 16. So that would explain why this p-value is so small that I don't even recognize this number. Remember, the E minus 42 is scientific notation. So this is essentially saying that there are 42, or actually 41 zeros in front of this one. So it is a ridiculously tiny number. We might as well round it to 0. So in fact, if we change it to a number and add digits to our heart's desire, we would see that it's just zeros. So let's go ahead and write that down on our picture. Let me see how good I can do with this drawing tool. Okay, so it looks like we've got an alpha value here. Alpha is 0.05. It's over on the right, inside here in this yellow area. Our p-value is very near, so we'll say approximately 0, which is definitely less than 0.05. Okay, our critical value is 16.92, and our test statistic is 200, so I have to make this tail longer. It is way over here. 221.346, and its value, which is a p-value to the right, is much, much smaller than this much larger area that takes up the whole tail. So this whole thing is alpha. Ooh, that highlighting got out of control. Just pretend like it's between the two lines. Okay, so we have our p-value, which is approximately 0, less than alpha. We have our critical value. Our test statistic is very much larger than it, so it's far over here into the right tail. So either way, we're going to reject. So going to step 7, we are going to reject the null hypothesis, which makes sense because we already realized that these sets of numbers are too far apart to be able to say that this is uniform, or that it's reasonable that 0 would have 47 occasions when other numbers had, less than 10. Okay, so we reject the null hypothesis for one of two reasons. We did both tests, p-value and critical value. So our test stat our test stat falls in the rejection region, which it did, or our p-value is less than alpha, which it was. So we have to go back up and figure out whether or not we support the claim. So we reject the null hypothesis. So if we go up here to the null hypothesis, let's go ahead and just highlight that red because we've rejected it. Okay, and then we're going to go to the claim and see if they match. So if the claim matches the null hypothesis, I'll turn it red too. And if it doesn't, then I'm going to turn it green because that means I support it. So I've rejected the null hypothesis. If the claim matches, then I essentially reject that as well. But if it doesn't, then I don't have to reject the claim. I support the claim, or the data does. So let's see. The last digit matches the uniform distribution. Or in other words, the last digit are all the same, or occur with the same frequency. Their claim is the digits do not occur with the same frequency. So I'm going to turn that green because I do support that. It's the opposite of the thing I rejected. So going back down to step 8, the data supports the claim that the digits do not occur with the same frequency. So in other words, it does seem like the value of 0 comes up too often. These numbers are not randomly distributed, and so we have, or not evenly randomly distributed. So we have too many zeros, so it was likely that this was not actually collected. It was estimated. There we go. That's the word I wanted. Okay, so I hope that helps with the homework. Sorry the video got a little long there, but if you have any questions, hit up the Hey Professor board or send me an email or contact me through Pronto. Hope to hear from you soon. Bye.